Okay, so this is the history. You could say that the history of distributed ledgers has had 4 generations. Each one has built on the previous one, and then each of them continues to evolve over time. But we could say that what we started with, in some sense, you could say Bitcoin started with cryptocurrency, which was a really cool idea. We can have an actual money with no government creating it. That's a bizarre concept, and no one person can destroy it, and no one person's in control, and that's really cool. And so what we started with was cryptocurrency, and it was revolutionary. And so, of course, what you have to have is some way to put the transactions in order, and you have to be able to agree on it. And so there's some kind of a store of information that we're all agreeing on, and we're using it to store our cryptocurrency transactions. There's this ledger thing, but then we realize, well, you know what? It's just ones and zeros. We can store other things beyond that. So you could say the second generation is when we realized, well, we can do more than money with these ledgers. We could put anything in it. We could store all sorts of information. We could store ownership rights of property. And so I could have my money in it, and I could have the deed to my house in it. I could have all sorts of things stored in this thing. And so it expanded what you can do. Not only do I have money, I now have other things like property and identity and other interesting things can be built on top of that. But you know, this starts to raise an interesting question. If I can store my money in this thing, and you could store your house deed in this thing, wouldn't it be cool if we had some way to swap without having a third party? The problem, of course, is that if I email you my money, you might not email me the property. And if you email me the property, I might not email you the money. We need a third party to take them both and then swap them and then put them back. But we don't want to trust third parties. So what we could do is have some kind of a program that runs on top of it that does arbitrarily Turing-complete interesting things. And so, of course, we have smart contracts. And so it was natural when you had a cryptocurrency to realize, well, there are ones and zeros, we could build a ledger. And then once you have a ledger to realize, you know what? We could do smart contracts on top of this thing. Everybody who's running the ledger could be running these little programs. And then we could be swapping all these different things that are on the ledger atomically. And we could be running arbitrarily complex programs. And so once we have the ability to have money and to have assets, and now to be doing these swaps so I can sell you something and you buy it from me, the next obvious question is, could you have a whole group of sellers and a whole group of buyers? Could you create markets? This would be the 4th generation. Could we do something beyond just simple transactions between 2 people and have large markets where there's lots of buyers and lots of sellers, and that there's some kind of a matching system that matches people up, like a stock market or a real estate market or an eBay, where you have multiple buyers simultaneously and do it in real time. Of course, to do that, you have to start worrying about fairness of how we match it up. So in a stock market, if everybody's putting in their bids on this stock, and you put in your bid, and I put in mine just a little bit later than yours, it would be a disaster if I could bribe somebody and get mine before yours. And so for this 4th generation, what we need to have is fairness of ordering. We need to make sure that if you put yours into it before I do, that it's actually going to count as being before mine, and that it's hard for me to get everybody to say that I did it first when really you were doing it first, when you were reaching the community first. And so we would say that fairness of ordering is where it's really reflecting when these transactions reach the community. In fact, you could say that is the exact definition. We could say we're going to put a timestamp on each transaction, which is when it reached the majority of the community. And then we'll put them in order by those timestamps. And then it becomes very difficult for any one person, like a leader, in a leader-based system, to reorder them, or to put them in an order that they like, or to just leave one out. It becomes very resilient to that. So you could say that these are the 4 generations. Now, of course, they call the 4th one markets, because that's where fairness matters. It's multiple people, not just 2 people. It's a large group of people all interacting in a way that is fair. But of course, that 4th thing can involve things that aren't at all a stock market, like games. So the same thing is applying to games. If you want to be doing a video game, an MMO, you need to make sure that if you shoot me and I dodge, we have to figure out which one happened first. Because if you shot me first, you get a point. But if I dodged first, then you don't get a point. And so we have to worry about that. And we have to worry about people hacking the client on their computer to try to cheat to get an advantage in this way. So that's the 4 generations of DLTs. You could say a lot of this 4th one also needs high throughput, but really all 4 of the generations are looking for high throughput. And security is important for all 4. So that's sort of a history of DLTs. Oh, okay. So we're going to do these slides. Let's talk about how this works. So Hashgraph can do the 4th generation stuff. It can do the fairness of the timestamps. The timestamp reflects when it reaches most of the people. Now, of course, if you can cut my computer off from the internet, it's going to take me a long time to reach everybody, and my timestamp will say that my transaction was very late. Okay, you could say, well, life's not fair in that way, but the timestamp is fair. The timestamp will still reflect when my transaction actually reached the community. Or if you have a faster internet connection than I do, then of course yours will reach the community faster. But the timestamp will be fair, it'll reflect that. So Hashgraph does all those things. Also, Hashgraph is fast. In some sense, it's kind of going at the limit of whatever bandwidth you have. And here's why. If we're going to build a ledger, we have to have these transactions spread out to everybody. Now, of course, we can go to multi-sharded systems. That's a good idea. But in order to have a fast multi-sharded system, you want the individual shards to be fast. And so let's talk about what goes on in a shard. Within it, every person has to receive every transaction. That's the bare minimum. We're going to have digital signatures. That's a bare minimum. And we're going to have timestamps. It would be very difficult to have a system with no timestamps at all and still get fair timestamps out of it. So this is kind of the bare number of, the minimum number of bytes that we're going to have to send over the internet. So you have to have enough bandwidth to receive each transaction once and to send each transaction once and to have signatures and to have these timestamps. That's the bare minimum that any system will need if we're going to have a replicated database of any kind. What is the fastest way to get that much information out? If that's all we're going to do, we don't even care about consensus, we don't care about ordering, we don't care about timestamps, all we care about is just getting the information out. What is the fastest and most resilient way to do that? And by resilient, I also mean let's worry about DDoS attacks. Could someone shut down one computer and stop us? That's the fear. So here's what we do. We do gossip. Alice has a message that's read here. She picks someone totally at random, and she gives it to Dave. Now 2 people have the message. Now Alice and Dave each pick somebody at random. Alice picks Gina, and Dave picks Bob, and now 4 people have it. And then each of them picks someone at random, and now 8 people have it, and then 16, and then 32, and it explodes outwards exponentially fast. If any one computer is down, still explodes outwards exponentially fast. Doesn't really hurt us. This is incredibly resilient. There's no one computer you can shut down. There's no bottleneck. It's not like we all have to funnel our messages through one person, that everybody gives their messages to one person and they distribute it out to everybody else. And it's about the simplest thing you can imagine. This is the simple brain dead, just do stuff random and it happens. So this is used everywhere. Lots of things. I mean, Bitcoin uses it for 2 different things. It's used everything for everywhere. This is the best way that you're going to get information out. And that's gossip. Then, of course, the question is, what happens if 2 people want to send a message out at the same time? Bob and Carol. So in a traditional database, distributed database, if you want an ACID database, we would have something like 2-phase commit. We would have locks. Or in a leader-based system, we'd have a leader that takes turns. Basically, we had ways of forcing them to take turns, where maybe Bob sends it out to everybody, and then when he's done, Carol can send it out to everybody, and then we know the order. But that's slow. They're having to take turns. What would be the fastest way to do it? Oh, well, it'd be this simple, stupid way of doing it. Just do it. Bob picks someone, Carol picks someone at the same time. Now 2 people have each of them. Then each of them picks someone. Now 4 people have each of them. Then each of them picks someone. Now 8 people have each of them. It just explodes outwards for both of them at the same time. Basically, with the internet, you're never going to get faster than this. This is as fast as you're going to do. And if all we're doing is spreading out our transactions with their signatures and their timestamps, this is the minimum number of bytes that we're ever going to be able to send over the internet. This is the baseline of what you have to do if you want a replicated information store of any kind. The problem, of course, is look at the order they received them. Bob received red, then green, then blue, but Alice got them in the opposite order, red, then blue, then green. So the stupid brain-dead way of doing it is really fast and resilient, but it doesn't give you a consensus on order. It also doesn't give you a consensus on timestamps. When did the community reach the get the red one? I don't know, everybody got it at a different time. That's not really a good way of putting fair timestamps. We could ask Alice, what timestamp did you put on your message, but she might lie. So this doesn't give you consensus on timestamps, it doesn't give you consensus on order, but it's incredibly fast and resilient way to get your stuff out. So then the question is, how do we get consensus? And the answer is, hold that question. We're going to do something else. We're sending out all this information in the most efficient way we know, and we're going to add one tiny little bit of extra information. When I talk to somebody and get all his information, and then I talk to you, I'm going to tell you the last message I received from him and the last message that I created. That's it, just 2 messages. Just pointers to 2 messages. So I'm going to have this big, long conversation with you. At the end, I'm going to create a big one of these messages, one of these events, and I'm going to include in it 2 hashes of 2 other messages, and that's it. This can be an incredibly tiny amount of information. In fact, there's ways you can compress these hashes down just a couple of bytes because it's a hash of something you already have in memory, and you don't have all that many things in memory. And so it's unique among, anyway, you can compress it a lot. So we're going to do that. So we've done the most efficient thing we can imagine. We're sending all these bytes over the internet, and then I'm adding, I don't know, 1% more bytes, a little bit extra. And that tells me nothing about consensus. Why did I do that? Here's why I did that. What we can do is draw a picture of how we talk to each other. So I'm imagining a world here of 3 people. We start at the bottom and go up. And what we say is, here is the event where Alice called up Bob and told him everything she knows. Here's the event where Carol called up Bob and told him everything she knows. And apparently Bob turned around and then talked to Carol and told her everything he knows. He also turned around and talked to Alice and told her everything he knows. And you can just follow up the graph. That is a history of how we have talked. Here's the magic thing. That thing about putting 2 hashes in every message, if they're referring to the last 2, the last one you created and the last one created by the last person you talked to, just by adding that tiny bit of information, you get this entire graph in memory. In fact, everybody does. Everybody gets the entire history of exactly how we talk to each other. In other words, we're not just gossiping about these messages that contain transactions. We're not just gossiping about messages that contain identity information or other types of information. We're going to gossip about this graph itself. We're gossiping about gossip. So the whole point of this graph is it's showing us the history of how we talked. And what did we talk about? This graph itself. We're talking about the fact that we've been talking about things, which is very strange. Gossip about gossip. But it didn't cost us very much at all. And what do we get? Every person has this graph in memory, and it's the same. Every person, any person who has this top event here, has the 2 hashes of these 2. Therefore, every person who has this one has exactly these 2. Every bit is the same. You can't, unless you can break the crypto system, the hash system, they must be guaranteed to be the same. And if you and I both have these, then you and I will both have their parents down here, and these 2. And so the whole graph has to be identical. So basically, if you have that one at the top and I have that one at the top, then we have exactly identical graphs below it, guaranteed. And what we have then is a history of how we've talked to each other. And so I know what you know. And I know when you learned it. And I know what you know about what Alice knows. And about when Alice learned those things, about what Bob knows. I can do really deep, complicated reasoning about what we know and when we knew it. I can do deep reasoning about our level of knowledge at every point in history. And I'm getting all of that information kind of for free. I'm adding 1% to my bandwidth cost. That's it. Okay, that's cool. But what good does that do us? We still haven't got to consensus. Now here's the magic part. I'm going to get consensus completely for free. At this point, I'm going to send 0 bytes over the internet, and I'll have consensus. Because I'm going to do virtual voting. Remember one of those earlier slides that said that the voting algorithms have these wonderful math properties? They are asynchronous, Byzantine, fault-tolerant. They are resilient. They are DDoS resilient. They can even, in some cases, have types of fairness, although fair ordering is far more difficult than fair yes-no questions. But they can have something like fairness in some cases. The voting algorithms are absolutely beautiful, and they predate all this stuff. They come before Bitcoin. They go back 30 years. These voting algorithms are fantastic, except for the slow problem that the voting algorithms have votes. And if there's 1,000 of us, and each of us is sending a vote to everyone else, that's 1 million votes going over the internet. And because you might be lying about your vote, we all have to tell each other what each other said, which means you now have 1 billion receipts going over the internet. And that's for one round. Then you have to have multiple rounds, so it's multiple billions. And that's just to decide a single yes-no question. Then we have to somehow decide a whole bunch of yes-no questions to put things in order. It's impractical. Huge bandwidth costs because we're sending billions of messages over the internet just for these votes and these receipts. But if I have a hash graph, I can do the voting purely in my head. I don't have to send any bytes at all over the internet for the voting part. All I do is I say, I know what you know, and I know when you knew it. And so if we were to run a voting algorithm, I know exactly how you would vote right now. So don't bother. There's no need for you to send me your vote. I know you would have voted yes on this question. So don't bother. I'll just pretend you've said yes, and I'll continue. And we can run the entire voting algorithm purely in our head. So that's virtual voting. So the hash graph consensus algorithm is gossip about gossip with virtual voting. And that's all there is to it. It's actually really simple. It's in some sense old-fashioned algorithms, voting algorithms that are wonderful, but with no votes. And we're doing it because we have a hash graph that shows us the whole history, but we got that almost for free by adding a tiny bit to the original thing. Oh yeah, and so what's inside of each of these? An event, one of these circles, has to remember the hash of the event that this line went down to, and the hash of the event that this line went down to. That's what it was supposed to say. And then, of course, you have transactions. Yeah, we do actually care about transactions. That was the whole point of this exercise. So when you create an event, if you have any transactions you want to create, just stuff them inside. That's it. They come along for the ride. They're just the payload. They just kind of ride along with the events. And then you have to have a timestamp, and you have to sign it. But you would have had to do that anyway. So these top three levels are the bare minimum that you'd have to have just to have distributed object stores that everybody knows the same data. And these last two are the extra overhead for gossip about gossip to get a hash graph. And then for the virtual voting, you send 0.